please.
Thank you for the introduction. So this is a joint work with, again, with Vincent Cruz and Rolf Niedermeyer. Sorry if I mispronounced the name. Anyways, so let me start with a motivating example for matrix completion program in general. Suppose that you have some service like Netflix, where a user can watch your movies. So unfortunately, for now, you have only 3 users named Alice, Bob, and Charlie. And then you have very unique titles named movie 1, 2, 3, and 4. And in this service, well, a user can give a rating for each movie that they watched. So for instance, you can see that Alice liked movie 1 a lot. And if you look at Charlie, Charlie liked movie 4 a lot. But it's also possible that, for instance, Alice didn't have any rating for movie 4. Well, it could be because she didn't watch the movie yet, or maybe she watched it, but she decided to not give any rating at all. So as a service provider, we would like to know in advance, before the user gives rating, how much the user is going to like the movie. Well, then if you can make a prediction, then you can maybe recommend the movie to the user. So yeah, so this is I believe that one of the most natural applications of matrix completion program. But the idea is that, like, you have a matrix where some entries are not observed or unknown, and you want to infer what the value should be for the missing entry. It's ubiquitous and has other applications, like in computational biology, where maybe a row is a DNA sequence and column is the position of the DNA sequence, and so on. So mathematically, we want to model as like we call such a matrix incomplete matrix. So for my talk, I assume that each entry of the matrix, say S is, so this Sij is the entry of S, where in the ith row and jth column. So each entry is either some symbol from the alphabet or it's missing. And for missing, we use the character star to denote that it's missing. So for instance, like in this matrix in the right, you can see that this matrix has alphabet 0, 1, 2, and four rows and 5 columns. And I marked the missing entries by red rectangle, red thick lines. And then, like, so we want to sort of complete this matrix. So by complete, what I mean is that we want to replace each missing entry by some character from the alphabet. So for instance, is in the matrix above S can be completed in this matrix T, where, say, first missing entry in the second row is completed by 1, and the third row second missing entry is completed by 2, and so on. So given this, we define a problem where we are given an incomplete matrix, and we want to complete the matrix such that the Hamming radius is minimized. So what do I mean mathematically is that, well, the input is again an incomplete matrix of n rows and l columns, and the additional integer r, which denotes the radius. And the question is to decide whether there's a completion of the input matrix such that there's some center row vector v, which does not contain any missing entry, such that the distance from each row is bounded by r for each row in the completed matrix. So let me show you an example. So this is an example with 4 rows and 5 columns, and radius is 2. And in the left, I have shown the input matrix, and on the right, what is shown is one solution. So here we set the solution center vector to be O1. And then we complete above is shown the completed matrix. And to make it easier to see, I denoted the cell dark. I marked the cell dark if it differs from the center matrix B as center vector B. So for instance, the second row vector has distance 2 from B, and the third row vector has distance 1 from B. So this is one solution with R is equal to 2. And in general, actually, it suffices to find the row vector V, because then each matrix, each missing entry should be completed so that it matches the B in the corresponding position. Okay. But then, so like here in this paper, in our paper, we consider the variant where we minimize the Hamming radius. Well, actually, we also consider a variant where we want to minimize the local radius, meaning that, well, I will not go into detail, but in short, what a local radius is that local radius is basically radius, but we have additional constraints saying that the center vector must be a row vector from the completed matrix. But it's not limited to radius. In fact, we have another work with the same authors that is studying the minimizing diameter variant. And moreover, there's also work in 2 years ago, which studied the variant where you want to compute, you want to minimize the rank of the completed matrix. And last year, there was also work that was studying the variant where you want to partition the rows such that the radius, local radius or diameter is minimized. Well, actually, this program is more general than what we considered. So our program is when basically clustering with one partition, like where there's one part with minimized radius, but the results are more of a classification result, and I think our algorithm are better in terms of practicality. Okay, so I will talk about like excuse me, some related work. So first of all, when the matrix is complete, meaning that matrix does not have any missing entry, it is known as the closest string. Well, there's bad news because it's kind of bad news because closest string is NP hard even if the alphabet is binary, and it's been known for a long time. But there's also good news saying that, well, there are many fixed parameter tractability results for closest string. So we wondered whether it's possible to sort of generalize what is known for closest string to our minimum radius matrix completion problem. And I also have to remark that there was the minimum radius matrix completion problem we call was also studied by someone else under the name closest string with wildcards. Okay, let's get to what is known and what we found. So to generalize what is known for closest string, we consider the parameter maximum number of missing entries in any row. So first of all, closest string is known to be solvable in R to the R time, where R is radius. And so like in my talk, I will just ignore the polynomial factors. So it can be solved in R to the R time. And we proved that, so generalizing this result, it was already shown that minimum radius matrix completion can be solved in alphabet size to the k times R to the R time. And we show that, well, actually, it can be solved in basically R to the R plus k time. Well, I have to remark that there was in this in TCS 2015 paper, there was some result, some algorithm of similar running time was claimed, but we found that there was a mistake in the paper, and we provided some alternative algorithm. And it's probably like this R to the R plus k, and this plus k is probably inevitable. And this is because minimum radius matrix completion is NP hard even if the R is equal to 2. This is kind of surprising because closest string is polynomial time solvable for any constant R. So you might wonder, what about R is equal to 1? Well, it was already known that it can be solved in polynomial time for a binary alphabet. Actually, we show that it's linear time solvable for any alphabet. And moreover, there's another result for closest string, which is faster for constant alphabet size. Sorry, this D, like alphabet size to be D, this D should be R actually. But we show that we can also adapt this algorithm to minimum radius matrix completion. So our main contribution is that maybe we generalized what is known for closest string to our problem. Okay, so I will show how to obtain this result of R plus 1 to the R plus k time algorithm. So to show this, we work with the more general problem, which we call constraint radius matrix completion. So the input is basically the same, except that we have additional numbers. So basically, radius can be specified for each row. And it's easy to see that minimum radius matrix completion is a special case of this problem, where I is all equal to R. Okay, so like our algorithm is a search tree algorithm, And in our branching, we make sure that in each step there's at most R+1 choices, and we also ensure that there's at most R+k branchings, resulting in this running time. So there's two cases when we consider two cases. First case is when R1 is equal to 0, and the other case is when R1 is positive. Okay, so let's start with the R1 is equal to 0 case. So suppose that we have suppose that we have matrix S and R1 is equal to 0. Then we remove the all columns where S1 has no missing entries, so known entries. So we just remove it and then update R2, 3, 4. So because like this is we can remove it because if there's a solution B, then the first two entries of B must be both A to match S1. So we also need to decrease R. So for second row, we decrease it by 1. So it becomes 3. And for the third row, we decrease it by 1. And for the last row, because it's AA and BB, so we decrease it by 2. Okay. Okay. And at this point, if Ri is so that for each row, if the number of non-entry is less than Ri for all rows, then we can just return yes, because arbitrary row vector is a solution. So if this is not the case, there is a row where the number of missing entries is, non-entry is larger than Ri. So let's pick some row, like we pick any row with such a property. And then we pick such a row, and for that row, we choose some columns, R+1 columns, where the row has non-entries. And then we branch. So by branch, what we mean is that, so for instance, if we decided to fix fix A as the first character of the row vector, then we decrease for each Ri by so because this is different, so we decrease it by 1, and for this guy also different, so we decrease it by 1, and moves on. And then, well, if you look at it, like if there's in each branching, there's at most R+1 choices, and K1 decreases by 1 in each branching. So let's get to the second branching to draw the drawings. So for the second case, it's a bit more complicated. So first we complete B1. We complete the first row vector in an arbitrary way. Let's say that we complete it by all A, which is shown below. And then we compute for each row vector what is the difference from V1. So for instance, in the second row, the second column and third column is different from V1. And then again, if the number of different positions is at most Ri for each row, then we can just return yes, because V1 is a solution. So suppose not, then there's a row, there's an I that violates this condition. And again, we use the same strategy. So we pick from JI some RI plus 1 columns, and we branch. Okay, so for each branching, again, we have R plus 1 choices. And well, this time R1 or DK1 decreases by 1 in each branching, resulting in an algorithm running in R plus 1 to the R plus K time. Okay, let's wrap up. So we've shown that for minimum radius matrix completion, there's an algorithm running in R plus 1 to the R plus K time. And well, I don't want to read this, but that there's another algorithm that generalizes the one for closest string. And we focus on that parameter, the maximum number of missing entries in any row. But actually, like, well, this is kind of nice thing about parameterized complexity. It's flexible, like we can be flexible about the choice of the parameter. So maybe we can also look at the maximum number of missing entries per any column, or the number of rows or columns where with some missing entries. And with that, I conclude my talk. Thank you.
Thank you. So are there any questions?